works, and 0 works. Okay? So that's you understand the concept. If you go small enough, it will work. If you go big, you could be lucky. Some of you said you jump to 0 and work. Great. But no guarantee there. Okay? Now, one thing you'll notice though, I forgot. Okay. Did you get 101,412? Some of you got different, right? How much vinyl chloride we made? We're supposed to make about 101,412. Some of you get slightly different numbers, right? That is because of the default setting of the adjust. The distillate of that separator contains all the vinyl chloride. And these are the component flows, and we want to make 101,400 pounds per hour of vinyl chloride. So you may get 102,000, right? So you can get it more accurate if you go to adjust and select the second tag, parameters, and you'll see here tolerance and step size. Just change the tolerance. Change, for example, the tolerance to 100 pounds per hour. Now you should see that it should go to 101,400. Pretty close to that. Just change the tolerance. Change it even smaller if you did. What are you getting instead of 101,412? Okay, change it to even smaller. Yeah, right. That's the accurate number, so it won't change anything. Did it change? Okay. Yeah, so you can decrease the tolerance to get it tight. So is the procedure clear? Yeah. So that's the main thing in the next step of your project for the chemical synthesis side. Okay? On the bioethanol side, you basically need to have done what we were with step 1, with the file 1, where you make the required amount of bioethanol. So that will set how much corn stover you should be feeding. Okay? All right. So the next step in the summary, and I will get off the computer now. The next step, although I'll come back to the computer for something.
That's crazy.
So we go now to step 4, separation processes. To keep the example simple, we will assume that we don't have to remove the leftover ethylene and chlorine. Let's say we just need 95% pure vinyl chloride, and this doesn't change. We still have 95% pure with. So we are going to ignore in our separation removal of chlorine and ethylene. But we have coming out of the cracking reactor 3 main components coming out, and we have vinyl chloride, we have dichloroethane, and we have HCl. And we want to separate those things. HCl is not small amount, right? We make as much HCl in moles as we make vinyl chloride. So we can't neglect that. And of course, we definitely want to separate the dichloroethane because that's what we recycle. So we need to decide that separation. We have 3 components.
Boiling point?
So what strategy we can follow? If you have 3 components and you use ordinary distillation, I have A, B, C. Let's order them in order of most volatile, least volatile. Okay? So in our case, what's the most volatile?
HCl.
HCl. What's the least volatile?
C2H4.
So this would be my A. This would be my B. And this is my C in order volatile. Okay? As we learn, one of the heuristics that is used in ordering distillation columns is the direct path in which you remove the most volatile component first. So what we would do here, we're going to use as keys HCl and vinyl chloride. So that means I'm trying to separate between those two. This will be my light key, this will be my heavy key. Yeah.
Wait, why is the second one not more volatile? I would say it's A, B, C. By weight.
Okay, let's continue. And then we'll have a separate. So here would come A, here would come B, C, and this would be the feed. The next second column will divide B from C. We could have ordered it, we could have done the first column between B and C, and the second column between A and B. We'll talk about some heuristics that will guide us into which sequence we should be following. But let's design a couple of distillation columns that will do this job following the path that I drew. So to decide on distillation column operation depends very much on pressure and temperature we're operating. Okay? So we need to choose for the 2 distillation columns that we're going to design here at what temperature and pressure we are going to be operating them. And to do that, we need to get some data first. So we're going to be looking at boiling points at different pressures, not just normal boiling. So you have 3 main components, and I'm writing them here in the order of volatility: HCl, vinyl chloride, and dichloroethane. And the normal boiling point is minus degree C. So I know we have kind of mixed units, but this is an example from the test that uses these mixed units. And it's not uncommon in industry to be using mixed units, okay? So the normal boil point of HCl is minus 84.8 degrees C. Vinyl chloride minus 13.8. And dichloroethane is plus 83.7. What happens now? This is our atmospheric pressure. Remember, my first reactor was at close to atmospheric pressure. I think it was at 1.5 atmospheres, right? So, and my second reactor is at 26 atmospheres. So, probably that's the range I should be interested in for the first column. So if we look at boiling points at different pressures, at 4.8 atmospheres, it's minus 51.7, 33.1, 146. At 12 atmospheres, of course, as we increase the pressure, the boiling point temperature of the pure components increases. minus 26.2, 70.5, 193. And the last pressure we are interested in is, of course, 26 atmospheres. We have the effluent of the second reactor at 26 atmospheres, so obviously we wouldn't have to do any pressure change if we're operating at 26 atmospheres. So that one has 0 degrees, 110, and 240. So I'm going to have this situation. Here is HCl, and I'm going to be separating HCl from vinyl chloride and dichloroethane. And if I wanted to do it in atmospheric pressure, do you see any drawback? Yes.
Why did you say 4.8 ATM was a pressure we should look at?
I have the data at these pressures, okay? I'm looking at some intermediate pressures between 1 atmosphere and 26 atmospheres. What do you think about choosing to do the first distillation column at 1 atmosphere, or close to 1 atmosphere? You see any drawback?
Have to freeze the product. Freeze them in like cryogenic a little bit.
That would be quite expensive condenser, right? Yeah. So that's the drawback here, yes. Well, that's the boiling point, right? And actually, what would be the pressure of the condenser? Sorry, what would be the temperature of the condenser if we're condensing? Let's say we have a total condenser and we're condensing at 1 atmosphere. It would be exactly minus 84.8. It would be the boiling point because there we would have pure HCl. Okay. Ignoring the small amounts of chlorine and ethanol. Okay, these are actually, we change things, but we're ignoring those in this analysis.
So you're saying at negative 84.
Yeah, that's what it would be, right? The higher the pressure, the lower the cooling cost. 0 degrees C, that wouldn't be that terribly expensive. A lot cheaper refrigerant, right? You wouldn't be able to use plant water for 0 degrees C, but certain refrigeration would be a lot cheaper if you need to be cooling at 0 to 0 instead of minus 85. However, you should always be checking on the other side what is going on. And on the other side, what is the problem if you have high temperatures on the other side?
A bomb.
What can why can high temperatures in the reboiler
You can break it down.
be?
You could crack your product.
You can have side products, absolutely, but there's also something else you should be watching out for. Approaching critical conditions. What do you have? What is distillation? Separation vapor-liquid. What happens to the vapor-liquid difference as I approach critical conditions? They disappear. The separation becomes impossible critical conditions, right? And becomes extremely expensive and extremely difficult as you approach critical conditions. So there are two things you need to be balancing among others. One is cost of cooling on the condenser, and the other one on the reboiler side, you want to avoid critical conditions. Also, typically the reboiler is run with steam. What happens to the cost of steam as I increase the temperature? It goes up, right? If you have steam if you need steam at 120 degrees C, That's much cheaper than steam at 240 degrees C. So that's something else that you need to take into account. So issues that you consider here, you have this trade-off, and maybe you want something intermediate, and let's say you look at the cost of refrigerants, etc., and you find out that probably this is much better than this, and let's say in terms of cost, this is not that much better than this. So you decide this in this manner to do the first column at 4.8 atmospheres. Okay. You can immediately figure out, so if I have 4.8 atmospheres, and of course every column has pressure drop, and where's the highest pressure point in the distillation column?
The beginning.
The bottom. And the lowest pressure is the distillate, okay, the condenser. How much pressure drop you have from one to the other depends on the difficulty of separation, but in most columns it's not going to be huge. It might depend on how many stages you have, but something in the order from 0.1 to 0.3 psi per stage is probably ballpark for most. There are always exceptions. Okay. So the pressure probably, we want the feed pressure to be close to 4.8, and might be the condenser might be 4.6, and the boiler 5.08, something like that. But we have approximate pressure for the column. We can consider approximate pressure for the column 4.8 atmospheres. So what would be the temperatures I would need? Well, for the distillate, I have pure HCl here, right? So the temperature would be the boiling point of HCl at, guys, I'm sorry, I made a mistake. I'm going to follow that. 12 atmospheres. Change that to 12. So we did the analysis, 12 atmospheres was the most advantageous. Change that, sorry. So it will be 12 atmospheres, so slightly less than 12 atmospheres in the condenser, slightly more than 12 atmospheres in the boiler. Okay. So what is the temperature that leaves the distillate? Very simply, very simple. Since we have pure component HCl, it will be the boiling point of HCl at 12 atmospheres. You can do calculations by hand on the basis of information, but of course, if you have a tool like Aspen or HYSYS or Unisim, you can immediately calculate it very fast using Unisim. Let's quickly do that. So I want to find the boiling point of HCl at 12 atmospheres. How am I going to do it? I'll simply create a stream that is pure HCl. So to find the boiling point of HCl at 12 atmospheres, I'll just take one stream, put it somewhere, click on that stream, I will specify composition pure HCl. Okay? I want to make sure you follow me on this. Click OK. And then I'll go to conditions. I'll put pressure 12 atmospheres. That's the pressure we want. So, who will tell me how I find the boiling point?
0 at vapor phase fraction.
That's a correct answer. As a matter of fact, any entry between 0 and 1 at vapor phase fraction is correct. Remember, the moment I specify that, I specify vapor liquid equilibrium. So it won't change. So put 0, as one suggested, you can say that the temperature is predicted to be minus 14.7, not minus 14.8, not minus